Good stuff. Okay, so there you are. You've been wooed by the student union candidates. They seem to take it quite seriously here. Campaigning, student union politics is quite a vicious thing. So I'm glad I'm no longer in it. So I had a few questions come in on today's meet, so I'll deal with them first. How do you go about creating an actual new database for the project? If you're using the Queen's Online hosting, you don't need to. You have a database created. It's called your first initial and your surname. Just click on that and use it. You don't need an entirely new database for this. Obviously, when you create the tables for this project, you might want to empty any tables that are already there, however you want to do it. If you're doing it on your own installation of MySQL, phpMyAdmin, there's just an option, new database, or the SQL for it is create database and then a name for it. There we go. Hi Dave, sorry I couldn't make it today. Hope you're having a fabulous day. Thanks. I needed that. So here's a question. And this is the first time this has ever happened in this direction. Can you change the project deadline to before Easter so that we can get it out of the way and relax over the holidays? That's the first ever time I've been asked to shorten a deadline on a piece of coursework. I'm afraid, I think the answer would have to be no. A couple of reasons for it. I've obviously given you the coursework and I've set a deadline of after Easter. To just turn around now and knock 3 weeks off it wouldn't really be doable for those of you that want to program it in. What I will say is that it's doable in a couple of days, I think. And that's not as in like I could do it in a couple of days. I knocked out the solutions in about 30 minutes, but then I wrote the test, so it's not, should be. It's doable in a couple of days worth of work. I know I've seen some students in the labs who have completed the implementation of the schema. You should have the test data out to you this week, and then next week some tests will be available, that kind of thing. So if you want to do it before Easter, I think you should go ahead and do it. I'm a firm believer in do it early and get it done. I always say to myself, next time I have a project, I will definitely start straight away. And then I'm sure, like a lot of you, I find myself the night before cursing my previous self for watching episodes of Futurama back to back that I've already seen and going to dog petting sessions when I should have been doing work. So no, I'm afraid we can't really move the deadline back. But what I would suggest is that if you start it, if you want a free Easter holiday, start it now, get it finished. Everything you need to do it will have been covered by the time we finish the practical next week. So we're now moving on to look at everything you need to do the creation of the tables, we've done. Everything to insert the data, we've done. Everything to exploit it, to do those complicated queries, the 10 queries you asked for. This lecture this week, the practical on Monday, and that'll be done. The 2 essay bits, the future planning bits, you're capable of doing those yourself now. What you might want to do is, if you do them now, is don't submit it, hang on to them, and then when we've done some lectures on redundancy and resilience, put those in as well. So I think you should, if you want a free Easter holiday, go ahead and do it now, and then rejoice over Easter. Eat chocolate bunnies or whatever it is that Easter is all about. There we go. When do we receive our results for the test? I'm really hoping, so the vast majority of you have passed, the initial sift has been done, data entry is ongoing. I doubt I'm going to get them out this week, but it should be out early next week, so within 2 weeks, basically just after 2 weeks of the test date. Will we have lectures after Easter? There is 1 week after Easter, which is, we won't have new material, but that's when I will do revision lectures. So we'll do revision lectures in week 12, Tuesday and Thursday, possibly Wednesday as well. And I'll give that will also cover having a look at the exam prep as well. Although I will introduce some of that to you before Easter, so if you want to revise over Easter, you can. What did you do last Thursday? I couldn't make it to the lecture. What? Something. Databases, I think it was, last Thursday. Schemas. We did schemas last week, so we carried on from the Tuesday, and we created schemas, new schemas, and then we would have done some SQL demos. The recording is online if you couldn't make it, as are the slides. Right, there we go. Good. So this week we're going to have a look at joins and inner queries, and some of the ways in which we exploit complicated data and merge stuff together and do that kind of thing. And this will go on today and Thursday, and then we'll look at some live demos on Thursday as well. So this is the kind of structure we're going to do. We're going to have a look at some of the joining theory. How do we join entities and tables together? and some other fancy stuff like Cartesian products, and then move on, have a look at inner queries as well. Obviously, I've already answered some questions on today's meet. If you've got any questions, ask them as we go along, and I'll try and have a look a few times and address any queries that you have. So to recap, to go back, all of these sessions, this is SQL 4 we're looking at, so we've covered the structured query language in quite a lot of detail, and we know what it's for. It's a domain-specific language to manipulate schemas and databases, and it has 3 types of scope: query, manipulation, and definition. And so far, we've seen all of them. So we started off having a look at query. How do we select data out of database? We then spent a week looking at manipulation. How do we insert, update, and delete rows and records in the database? And then last week, we moved on to definition. How do we create schemas? How do we change them? How do we add keys and indexes and all that kind of stuff within the table? So we've done all of that. And what we're now going to do is we're going to jump back to the start, and we're going to revisit querying data, but we're going to look at complicated queries. So we have seen simple queries. Give me all the data from this table. Give me all the data from this table whose name is Bob. Give me this column from this table where a certain condition is met. But always operating on a single table. So the theory then behind all of this that we're going to cover this week is all about relationships. So the key, again, is the relational part of relational database management systems. The core and the strength and the power of these databases is that things relate to everything else. We start off with a conceptual vision, and we have entities, and we know that the entities have relationships, that customers may have 0 or more orders, car may have a certain number of drivers, it may have a certain number of services. An owner could have 0 or more pets, but a pet must have an owner, or might not have an owner if it's gone wild. A customer might have orders, but every order must have a customer. You know, these relationships that we start with conceptually and then we map out, we create in our database. And we have tables which have foreign keys, and we have tables where elements relate to each other. And we've now created, we've gone all the way from our sort of logical model that students have classes and a student can be enrolled in these classes, and we mapped it all out. We've gone all the way now that we've created our database. We have lots of tables, we have lots of relationships, and we have lots of ways of looking at data. And when we create these relationships, we do it in SQL. So you saw that last week we use foreign keys. So here's an example. We create a table customer. We have an ID and a name, pretty straightforwardly. We have an order table, has an order number, but it has also a customer number. And what we're telling it is that the customer ID references the ID field in customer. So we're creating in our schema, when we put that in, we use the foreign key constraint. We're creating a constraint and we're saying this entity, this table, has a column that relates to this other table, to instances of that table as we go along. And we often want to refer to these relationships. Now, these relationships might be codified in schema. We might have said, here's a foreign key, here we go. We might not have done. We don't always have to do. We might have one set of schema tables and a total other database we're looking to relate things to each other. So when we exploit data, we need some way of saying, this table relates to that table, here is the way in which they work, and here's how we go together. And we accomplish this using the join operator. And what we do is we create basically a new virtual larger table. So we're joining these tables together to create an output that's a much larger table that we can see as we go along. We can use different types of ways to exploit the data as we need to do it. One of the other topics we're going to cover this week is inner queries, sometimes called subqueries or nested queries, depending on how you feel about it. And the idea of this is that we understand a concept. And the concept is fairly simple. The concept is that everything in the database is a table. So here is a table of data. When I run a select query on it, the result that comes out is another table. It's a virtual table. If I select certain columns, it's another table that has less columns than the source. Maybe it has less rows because I've used a where query. Whatever I want, but everything we create, when we run a select query, we are just creating another table, a virtual table of the output of the matching data that we want out of it. So here is our source table, ID, name, and phone, and 4 records within it. We can say select name from contacts, and we will get out one column with the contacts in. And this is a new table. We have created effectively a new virtual table which has one column but 4 records in. And we can also filter for the rows. So we could say select from contacts where name equals Bob. And we get out another new table, different new table. This time one row, put all three of the columns in. So each of these select queries that we run generates a new table, a new virtual table of data that we get out the other end. Now what this lets us do is it lets us run queries on queries. It lets us run a query, generate a virtual table of results, and then run another query on that table, and another query, and another query, and another query. So we can use the output from one query as a virtual table to run on another query as we go along. So an easy way to look at this would be, here's our source table, and what I want is I want just the name where the record equals Bob. Now, of course, you all know how select works. This was weeks ago, so you could write in a select query, but we're going to do it a slightly different way just to sort of show the point. We're going to do it in two different selects. What we're going to do is we're going to transform this data one way, and then we're going to use that transformation as a source to look at the data somewhere else. So here is our source table, and we only want one column, so we select name from columns, from contacts. So here we go. That generates a virtual table. The results from that query are one column and 4 records, and we only want one of those. So rather than doing that, what we can do is we can just say select star from what's the table that we're using. Well, we're no longer using the contacts table. What we're actually using is an inner query. So we say select star from brackets select name from contacts. So we're using this query here, the same one we used here, as a source table. So we're saying select from the results from this table where name equals Bob. So what we're doing is we're running a query, surrounding that in brackets, and then using the output of that as another query. All right, so this is just the introduction to this. I'm covering it now. We'll come back to it on Thursday, no doubt, and we'll have a look at greater detail. But conceptually, when we run a query, we get a table out, and we can then run other queries on the results of that query. We can keep going. We can use queries within queries within queries. So let's go back and have a look at joins. So an SQL join is a way of saying, I want you to join this to that in a particular way on a given relation. Here are two tables, this and that, students and modules, students and enrollment, students and marks. And I want you to join those two tables together. I want you to join students and enrollment together in a particular way, and we'll come on to what I mean by that. And what's the relation? What is the field that I use to join them? So in my enrollment table, I might have a student ID field. In my student table, I have a student ID, and I can say, okay, these two are the same, so we join them together to use them. So this was our example. Let's think about this. We have a customer and a booking schema here. So we have a customer table, ID and name, primary key, and then we have a booking table, an ID integer, a booking date time, and critically a customer ID, which is a foreign key. So the customer ID references customer ID. So hopefully that's all fairly straightforward. We have a customer table, we have bookings, and every booking has a customer that it's linked to. Customer ID in booking relates to the ID field in customer. When we create it, that's what we put in. We can't insert a booking that doesn't relate to a valid customer, but let's look at how we pull that out the other end. So here's some customer data. Here is some booking data. These are single tables, and we will be very adept now and very able to exploit and use individual tables to get the data out from one of the tables at a time. So how do I list all the bookings? Select star from booking. Lovely, all right. So this is what we're used to. We select star from booking, we get a list of all of the bookings within our booking table, it comes out, but it's not really very helpful, because if I want to know who has booked a table for 6 o'clock, all I've got is a numeric customer ID, so I will then need to go off back to the customer table to look up who is that customer ID to find out the customer and get their phone number or whatever to ring them and tell them their table's cancelled. So that's exploiting data from a single table. Wouldn't it be good if we had a way of exploiting data and reading it from multiple tables at a time? So one approach to doing this would be just to follow that process. We are not usually interacting with databases using SQL. Very rarely, it's a very bad system if we have to fire it up and write SQL queries to actually find out who is booked into our restaurant table that night. We're using a nice little web interface or a Java program or something to do it. So we could get our code to do it for us. So we could say, okay, go ahead, go and get all the bookings, get the customer ID for the booking that we're interested in, or each booking in turn as we go along. Go and look up the customer name from the customer ID, so do another query to the database to get the customer name with an ID of whatever. And then finally display the results. So we could run that in code, we could run that in our Java, in our SQL, in our PHP, in our Python, in whatever. Get every booking, for each booking execute another query, look up the customer, print it out nicely. Okay, and it would work fine. As far as the user was concerned, that's what they would see. They would see booking 6 o'clock, name Dave. They wouldn't realise that behind the scenes we'd got a number and done a lookup and everything. That's all very well and good, but it's not a very efficient or effective way of working. It's not very quick. We're having to do lots of queries every time, and we'll have to hammer the database. So what we want is a way to make the database do the work for us. We already know how these two tables are related. The customer ID field in the booking relates to the ID field in the customer. So we can do a query like this. So this is a very simple SQL join. Select star from booking, all right, so we know what we're doing there. Give me all of the records from booking. But now this is the new bit, so I want to join customer. So I want to join the customer table with the booking table. What do I want to join it on? How is it related? On booking.customerID equals customer.id. So give me all of the booking records, join them, each one, to the customer records. How are they related? Booking customer ID relates to customer.id. Give me everything in booking, relate it to the customer table, and this is how the two are related. This is how you look up from one to the other. We run that query, and what we get out is we get out a table which has more columns suddenly. Because we have the columns that come from booking, and we have the columns that come from customer. So over here we have the normal 3 booking columns, booking ID, customer ID, and booking from the booking table. But now over here we have customer ID and customer name from the customer table, which is exactly what we were asking it to do. Give me all of the bookings, select star from booking, join on the end, the customer table, and it is related where the customer ID equals the customer ID in the customer table. So we go through and we find a record, ID1, customer ID1 booking, and we will join on the record that matches customer ID1, which is Dave here, ID1, ID3, ID4, and so on and so forth. So that is simply, in syntax, a straightforward join in a join. Join customer to booking, join student to enrollment, join car to driver, join car to insurance, join this to that on this relationship. This is how this is related to that. And we specify out, we do it, we run it, and now boom, suddenly all of the data is available for us to go into. And that's a pretty full-on table, so we may well want to just filter, because all I really want to know is who's booked at what time. I don't really need to know what our IDs are and all of this kind of stuff, so we can quite happily specify it. We can say, okay, I only want 2 columns. I want customer.name, so I want the name field from the customer table. I want booking.booking, I want the actual booking date and time from the booking table. From booking, same join, it's the same way related, and now what we get out is this nice table at the other end. So in one query, we have asked the database to give us what we want out the other side. So instead of having to go, give me all of the bookings, who's this customer, who's this customer, who's this customer, who's this customer, I'm able to just say to the database, in its brain, let it do the work, give me the bookings, oh, and by the way, tag on the relevant customer detail, oh, and by the way, this is how they're related. Because computers are really stupid, and they don't often understand quite how things are related to each other. So that's it. That's the fundamental syntax of a join. And what you'll find as you go through life as database admin people, programmers, software developers, is that you use a lot of these and they get increasingly complicated. And there are lots of different ways. We're not done yet. We're going to have a look at a few different ways of doing it. But fundamentally, fundamental point, here is one table. Here is another table. Join them together, and this is how they're related to each other. That's it. Give me more data out. We write this. We write complicated queries. The data comes out. We don't need to post-process it. We've already got the data we need. We've got the extended data we need. And off we go. And we can put it in. So that's it. That's a join introduction. I'll have a quick look and see if anyone's screamed a question. Where's the information about project? It's all on Queen's Online, I hope, isn't it? Yeah, the project brief, it's on Queen's Online. Ask any questions on the forum. From next week, can we use Wednesdays for assignment help? Maybe. I mean, I'm not that convinced how useful this kind of setting would be for help on the assignment until you've all looked at it. What I would suggest that what we do is have a look now at the assignment, figure out what bits you're not sure about, raise those queries on the forum or on here or send me an email. I'll have a look, and if there's any common questions that come up, any common issues, we will by all means cover that. If I have to use a Wednesday, I will. I'm here, I've got no problem with that. What I don't really want to do is get in the habit of using Wednesdays where people only have to come in for that, because I think it would be a bit unfair to just say to people, oh, if you happen to live closer, you're going to be able to come in otherwise. But we'll use Wednesdays if we have to. How does one make a .mv database file? No idea. I don't even know what one is. I don't really understand these computers. I don't know anyone know what the file format .mv is? Not come across it. I think MDB is the file format for MySQL, or I don't know. Anyway, I'm afraid I don't know. I haven't come across that. Okay, so that's the fundamental concept of a join. And of course, nothing's ever simple. So there are actually lots of different types of join that we can do. So what you just saw there is a straightforward join, or what's called an inner join. Inner join says, I have two tables, they are related, give me the records that exist and line up in both of these tables. So give me the records where there is both a booking and a customer and they're both valid. It is the intersection in terms of set theory. I told you set theory would eventually be useful. So the inner join, the intersection, give me records where the record is valid in both entity A and entity B, in both table 1 and table 2, in customer and booking, and give me the intersection between them. So we're only going to get valid values where records are in both and they coalesce and exist between each other. So that's an inner join. That's the standard join we've seen. There are other types of join. So a left join. Give me all of the records in the left table. Give me all of the records in the left table, and if there are matching records in the right table, give me those. If not, give me null values. So give me all of the bookings, and if a customer record exists for that booking, great, give me a customer. If not, give me null values. Give me all of the enrollments, and join that with students. If a student record exists for that enrollment, give me the student. If it doesn't, give me null values to come out. Now in this case, we're selecting from booking, and we're doing a left join and going into customer, and because of our constraints, we have no null records. I'm saying select star from booking, left join, customer on, and giving it the customer details. So in this case, here are the bookings. Bookings are the left-hand side table. Customer is the right-hand side table. But because of our constraint, because every booking must have a customer, there are no cases where a booking is found but no customer is found. However, if we reverse the way the tables work, if we say here, select star from customer, left join booking, so now instead of this being booking and this being customer, this is customer and this is booking, what am I saying? I'm saying give me all of the customers join them to bookings, and if no booking is found, give me null values. So remember, every booking has a customer, but does every customer have a booking? No, they don't. So here we go. This is what we'll get out when we select from the customers. So the first thing is that there's going to be a row for every match between the two. So I have 2 bookings under Dave. So here's the first booking and the second booking for me. Jim has a booking. So there's Jim's 1 booking. Alice has a booking. That's her booking. But Sarah, customer ID 2, doesn't have any bookings. But I have said left join and customer is on the left. So I want every customer regardless of whether or not they have a booking, which is the entity B. So in this case, Sarah's come out and Sarah has no bookings, so has null values in all of the booking fields. So left join, give me everything on the left, matching data if it exists on the right, if not, null those values out to come in. Right join, fairly conversely, the absolute opposite of left join. Right join, give me all of the records in the right table and matching records to the left otherwise are null. So here, if bookings on the left, customers on the right, we get the same results out. We get the 4 bookings with the customers and then we get the null answers at the bottom because Sarah doesn't have any bookings to go on. So, fundamentally, this is it. Inner join, the intersection, only give me records where tables exist, rows exist in both A and B that match. Only give me customers that have bookings. Only give me bookings that have customers. Left join, give me all of the records in the left, give me all of the customers, line them up with bookings if they're present, if not, give me null values. Right join, give me everything on the right, give me all of the bookings, give me customers if they match, if not, give me null values. Inner join, left join, right join. Simple. It will become clearer when you actually start writing SQL and pulling it out of databases. Trust me. This is one of these things, one of the many I keep saying, trust me, it will all come clear. For 2 of you, maybe it will. But this is one of these things that certainly when I first got into it, a bit like classes in coding, I kind of thought, oh, it took me a while to get a head around until I actually started looking at data and actually writing exploits of data to come out. And then the penny dropped. So finally, one of the other options is we can do a thing called a full outer join. Give me all of the records in A and all of the records in B. I don't care if they intersect or not. If records exist in A but not in B, null the values for B. If records exist in B but not in A, null the values in A. MySQL doesn't actually support full outer join, but I'm including it here because if you look at joins online, you look at the Wikipedia article, which I don't just steal from my lectures, you will see that full outer join is included. So, inner join, give me the intersection. Left join, give me everything on the left. If records match on the right, great. Right join, give me every record on the right. If records match on the left, great. Outer join, full join, give me all the records, and if they match, great. If they don't, null the values as it goes along. There are some other fiddly ones that we'll come on to, which you don't really have to worry about for the minute, but we can say, I only want the right ones, I want the set only. I only want to come out with the details on the right that don't intersect. So this is again going back to the set theory we did in week 2-ish. This is a set difference. So I'm saying in here, I'm saying I want B set difference A. I only want the records that exist in B but do not exist in A. So fairly simply, we do a standard right join, but then what we do is we tell it, I'm only interested in those records where the left entry is null, i.e. there's no record found. So in this case, all we would get out is Sarah, the only customer that has no bookings within it. All right, I won't ponder on this too long because it's easy to get confused with all this, but the critical thing is inner join, left join, right join. These are the ones really that you need to remember. And obviously, we could also do left only as well in terms of getting the set difference out. Lovely. Piece of cake. So let's have a look at some examples. Let's try and bring this to life and see what they look like. So I've created here 3 tables. Our library system. We have a book. Books have an ID, a title, and author. ID is an auto-incrementing integer. We have a borrower, borrower ID, auto-incrementing integer, primary key. And then finally we have a loan. Loan is the link table, and loan just has a foreign key of book ID and a foreign key of borrower ID. So hopefully it's fairly self-explanatory. We have books, we have borrowers. They exist independently of each other, but there is then a loan table in the middle. Every loan is recorded that we have a borrower and a book ID, who's borrowed what, and that shows that someone has borrowed the book. Oh yeah, look, some arrows there. So book ID is linked to the book ID in book, and borrower ID is linked to the borrower ID in borrower. I'm going to tongue-tie myself, aren't I, today? The borrower borrowed. So there we go, fairly simple database, three tables in the schema, two options, many-to-many relationships, so we have a link table in the middle. So I've shortened them down. These are going to remain on the screen, so as we go through these examples, we can explain them to you. So this is a shorter version of the three tables, and I've also added some data in. So here are 4 borrowers created in the database. 4 books. 3. Oh, these are lined up badly, aren't they? I'm sorry. So 4 borrowers created in the database, 3 books, and several loans. So person 2 has borrowed book 1, person 1 has borrowed book 2, and person 4 has borrowed book 3. So this is the sample data, and this will stay up here on the screen so you can kind of see it as we go through, and hopefully it will make it a little bit easier to understand these examples. So let's have a look then at a couple of real-world queries, how we do it. So first question is, give me a list of names of people who have current loans. So I could say, if I said to you, give me a list of the IDs of people that have current loans, great, select borrower ID from loan, right? No problem at all. But I've specifically asked for names. So we need some way of relating the tables together. So here's our query. So what am I interested in? Well, all I actually want out is the name of the borrower. So select borrower.name from borrower. So give me the name of the borrower from the borrower table. Inner join loan on loan borrower ID equals borrower.borrower ID. So inner join, remember, only records that exist on both the borrower and the loan table. So we're only going to get records that have a current loan record against them. And we're joining the borrower ID in the loan table with the borrower ID on the borrower table. So we execute that, we go through quite simply, and what we get out at the end is a list of borrowers' names where those entries exist within the loan table only. Good. Stunned silence, that's what I like. So give me the name of the borrower from the borrower table. Join it with the loan table, so I know what loans have come out. How is the relationship met? Well, okay, in the loan table, there's a borrower ID column, and in the borrower table, there's a borrower ID, and those two are the same. And I only want an inner join because I only want those records that exist in both tables. So only where there's current loans out. Your turn. What's the query? To give me a list of the titles of books that are currently loaned. Pens and paper at the ready. Off you go, I'll give you a couple of minutes. If you want to cheat, you can. I don't bother with student demos of this, student versions, but have a look. What do you think, logically, you would do? What are you asking for? What's the relationship you're mapping? What type of join is it, and how are they related? Off you go. Or just walk out. Okay, no one else has walked out, so that's good. I regard that as a success if only one person walks out per question that I ask. There's 400 questions left to go. So hopefully you had a good stab at it. So let's have a look at what I think the answer is to that. So I want a list of the titles of books that are currently loaned. So this would be my solution. Select book title, so that's what it's asking for, from book. All right, so a fairly simple query. That would just give me all the titles of the books. But I want to join it with loan. I want an inner join because I only want those records that exist in loan and in book. And join on that book ID field in loan is equal to the book ID loan in book. So there we go. Join those two tables together. This is how they're related. These are the tables we're joining, book and loan. And it's an inner join in that I only want the two of them together. Someone just asked a question on today's Meet, are the left and right tables exactly the same but flipped? No. No, the left and right tables are whether they're on the left or right of the query. So in this case, the left table is book and the right table is loan. So it's just whichever one comes first. If you wrote this out on one long line, the left-hand table is the one furthest left and the right-hand one is further on. So the table we mentioned first is the left. We read from left to right. The table we mentioned first is the left. The table we mentioned second is the right. All right, so hopefully some people had an answer similar to that. No? Yes? Yeah, I'm going to take one nodding head there and take that as a yes. Everyone's happy. Okay, good. Two nodding heads. Oh, good. Right, that's fine then. Okay. If I can just reach two of you, then they'll fire me. So, okay, there we go. So that's one query. All right, so let's have a look at another one. So this is a little bit more complicated. Give me a list of the titles of books that are currently loaned and the names of the borrowers who have them. So it's a slight trick question. I'm not going to ask you to do this, but what I'm going to show you is the power of joining. So I've shown you that we can join two tables together. So we can join borrower with loan, book with loan. Well, there's nothing to stop us joining borrower with loan and loan with book. And now we have all three tables joined together that we can exploit and we can query. So what do I want? I want a list of the titles of books that are currently loaned and the names of the borrowers that have them. So I need to, in my query, use the book table and the borrower table because I need the titles and the names, and I need to use the loan table to link them together. So what's that query going to look like? It's going to look like this. So we're now getting into longer and longer sort of select queries. So what is it we're asking for? That's the easy part. Oh, can't work a pointer. Select borrower name and book title. So that's what we're after. So here we go. From book. So books are first left item. Join that to loan, inner join on book ID equals book ID. Great. Okay, so that bit's fairly straightforward. So that's the first one. And now let's inner join borrower as well. So with loan now becomes the left, borrower becomes the right. So we're joining to that borrower on borrow ID equals borrower ID. So we're saying here, take book, join book with loan. Here's the relationship. Take this new table we created, which is the book and the loan together, and join that with borrower on the borrower ID being created. Join all those together, make your Franken table, and select the name and the title fields out of it. And this is, oh my God, I've lost the plot today. This is what we get out at the bottom. So we've got all the books. We've joined with loans. It's an inner join, so we're only going to get books where there are loans valid. We've joined the loan with borrower, and again, it's an inner join, so we're only going to get ones where that is valid. And we've taken the title and the name, and we've output them out the other end. So we can do an infinite number of these joins, because everything comes out as another table, and we can put them together, and we can mesh them together as much as we want. So how would we get something like a list of the names of borrowers that have no books currently loaned? So this goes back to, if you think about it, okay, this is a set difference operation. This is where we have books or borrowers, loans, and I want borrowers that exist but don't have any relationship with loans at all. I want a set difference of A to B here to come in. So that we can do that in a couple of steps. The first one is let's visualize what we actually want. This doesn't actually give us what we want. So if we do this query, if we say select borrower name and loan book ID from borrower, do a left join, so we're not interested in the inner join now, we want everything in the left. So we want everything from borrower and join it with loan, and this is the relationship. What we get out is we get every record in borrower. If there's a loan, sure, we get a loan value, but if there's no loan, because we're doing a left join, not an inner join, we get a null value for the loan to come out. So if we do a left join, we'll always get everything in the left, we'll always get everything in borrower, whether or not there's a loan, and when there isn't a loan found, we'll get a null value. Well, what was the question we were asking? The question was, tell me the borrowers that have no books. There are 4 borrowers. Sarah has a book, Jim has a book, Joe has a book. Betty, though, has no books, and we know that because she has a null record in the book ID field. So all we need to do to actually produce that query is update our query, add a where clause. We have exactly the same query. Select from borrower, left join loan, blah, blah, blah. But we're now saying where loan.bookid is null. So this was our result without the where clause. We got all 4 borrowers. Betty had a null value. We put a where clause in saying where it's null, and then boom, we just get her out the other side. Easy peasy lemon squeezy, as they say in database school, which I definitely went to. Okay, let's have a look and see if any more questions have popped up. Not that I can see, but it might be the Wi-Fi being terrible. No. Okay, jolly good. I think what we're going to do is, has anyone got any questions that they want to ask here now? You have? No. No, I don't. No, I don't believe so, but we'll try it out in SQL. Excellent question, thank you. I'm fairly sure not, because it's just a straight relationship. All you're saying is this equals this one. Obviously, greater than or less than comparative, it would make a difference. Okay, well then, with that, I thank you.